Electronic configuration. Electronic configuration describes how electrons are distributed among the various orbitals of an atom. It can be illustrated by SPDF notation or orbital diagram. SPDF notation denoted by writing the symbol of the subshell. Add the superscript to show the number of electrons in that subshell. This is the symbol of the subshell. Energy level N equal to 1 for atom hydrogen, N equal to 1, and when the subshell L equal to 0 means the subshell is subshell S. So this is 1s. The total number of electrons in orbital must be the superscript of the orbital subshell. So 1s, 1 means there is 1 electron in 1s orbital. The energy level is 1 and the subshell, the orbital is type s orbital. This is how we write the SPDF notation. And electronic configuration can also be illustrated by orbital diagram. Each orbital represented by box or line. This is how you draw the box and state the subshell or the orbital, or you can draw one line and state the subshell. The arrow indicates an electron present and its spin. So if you have one arrow, it means in this orbital you have one electron. If you have two arrows, means two electrons. And the spin, if the arrow is pointing upwards, it is positive half. The S is positive half. If the arrow is pointing downward, the S equal to negative half. Or you can also say that the positive half for pointing downward and negative half for pointing upward. It doesn't matter as long as these two are different. Rules for assigning electrons. You have to follow 3 rules: AUFBAU principle, Pauli's exclusion principle, and HUND'S rule. For AUFBAU principle, AUFBAU states that orbital with lower energy is always occupied by electron first. If you want to fill the electron in the orbital, you have to fill the electron into the orbital which has lower energy first. Which one has lower energy? It has to follow this order. 1s has lower energy than 2s, obviously because the number of n is smaller than this number of n. But when we have the same number of n, 2s orbital is lower energy than 2p orbital. 2p orbital has lower energy than 3s. 3s orbital has lower energy than 3p orbital. So if you want to fill the electron into the orbital, you have to fill into 1s first. And then the second electron fill into 1s again, because one orbital maximum electron can be filled or 2 electrons. If it's 1s, if 2p, maximum number of electron 6, because you have px, py, pz. But in S, maximum number of electron 2 electrons. That is AUFBAU principle. Fill the electron into the orbital which has lower energy first. Second rule, Pauli's exclusion principle. There are 2 rules in Pauli's exclusion principle. An atomic orbital hold a maximum of 2 electrons and they must have opposing spin. As I've mentioned before, for example in 1s only 2 electron maximum, and opposing spin means 1 electron must pointing upward, one more electron must pointing downward. That's what it means by opposing spin, clockwise or anti-clockwise. No two electrons in the same atom have the same set of 4 quantum numbers. If you remember, the set of quantum number is in bracket NLMS. That is the set of quantum number. So one set means that is assigned for one electron only. So that is no two electrons in the same atom have the same set of 4 quantum numbers. They must different. HUND'S rule. Electrons with equivalent energy or degenerate orbitals tend to occupy the orbital singly first before pairing up. Can see the HUND'S rule details in the next slide. So this is AUFBAU principle. Orbital with lower energy is always occupied first. So which one is lower? If you want to identify which orbital has lower energy, you have to construct this diagram. How to construct this diagram? You just put the number, start from number 1 until number 6. You write it vertically, 1, 2, 3, 4, 5, 6. Write it vertically and then put all S vertically. And then second, you put number 2, 3, 4, 5, 6 because this is for p orbitals. We don't have 1p because p is L equal to 1. When L equal to 1, n cannot equal to 1. That's why we start with 2p and then 3p, 4p, 5p, 6p. And then d orbital, you start with 3. So you must put at the same level. If 3 is here, so it is this level 3, this level 2, this level 1 energy level. So we don't have 2d because d is when L equal to 2. When L is equal to 2, n cannot equal to 2. That's why we start with 3d and it goes on 4f, 5f, 6f. And draw the arrow from the most right at the top part to the most left to the below part. So this is how you draw the arrow, 1s, 2s, and then from here, from the most right on the top part to the most left below part. And the arrow goes on. And if you follow the arrow properly, you start with here 1s. So 1s has the lowest energy, and then if you follow the arrow, there's no value here. So when there's no value here, continue to the next arrow. Next arrow, follow the arrow direction and you'll find 2s. And write 2s and then follow the arrow direction, and there's no value here, continue with the next arrow. The next arrow shows it's 2p. Start with 2p and then follow the arrow direction. After 2p, 3s, and then no value here, continue with next arrow, 3p, and then 4s, and no value. So that's why we have 1s is less than 2s, less than 2p, less than 3s, less than 3p, less than 4s, and so on. This is how you identify which orbital has lower energy, which orbital has higher energy, so you don't need to memorize this order. AUFBAU principle, more on AUFBAU principle. This is the energy level of orbital for lithium atom. Obviously, n equal to 1 has the lowest energy because it's n equal to 1. And then higher energy n equal to 2, higher energy n equal to 3. For n equal to 1, we only have 1s orbital. And then after 1s, we have 2s orbital. And after 2s, we have 2p. If you refer to here, after 2s, follow the arrow until no value on the left, continue with the next arrow. So that's why after 2s, 2p. Means 2p has higher energy than 2s. So that's why this is the y-axis, shows the energy. 2p orbital position is higher than 2s position because 2p has higher energy than 2s. But 2px, 2py and 2pz is at the same level. It means px, py, pz or 2px, 2py, 2pz has the same energy value. So that's why they are at the same level, because they have the same energy value, px, py, pz, because they are all p. They only have different orientation, but they still have the p orbital. Then 3s higher than 2p, 3p higher than 3s, and again 3px has the same energy as 3py and has the same energy as 3pz. This is for lithium atom. We know that lithium atom has 3 electrons, 3 proton. Z equal to 3 means 3 proton. The number of proton is equal to the number of electron. So our electron, we have 3. If you have to show the SPDF notation of Li, this is how you write down. 1s2 means 2 electron in 1s orbital, and 2s1 means 1 electron in 2s orbital. You start filling the electron at the orbital which has lower energy first. And the orbital diagram, this is how you draw it. Orbital diagram, box, draw the box or the line is fine, and then state or name the orbital 1s, and then draw 2 arrows to indicate 2 electrons in this, and then 1 electron in 2s, so 1 arrow only. Pauli's exclusion principle. An atomic orbital hold a maximum of 2 electrons and they must have opposing spin. We know that in s orbital only 2 electron maximum, but in p orbital we have 6 electron maximum because we have px, py, pz. In one type of orientation we can have maximum 2 electrons. Atomic orbital means in one type of orientation maximum 2 number of electron. So 2px 2 electrons, 2py 2 electrons, 2pz can hold 2 electrons as well in maximum. And no 2 electron in the same atom have the same set of 4 quantum numbers. Means we have this, if you have the electron 2, if you have 2 electron in total, the electronic configuration 1s2. Okay, you start filling the orbital which has the lower energy level first. So 1s2 means 2 electron in 1s orbital. That is how you write the electronic configuration or SPDF notation. And this is how you draw the orbital diagram. 2 electron in 1s orbital. 1 electron pointing upward, 1 electron pointing downwards. That's what it means by they must have opposing spin. 1 upward, 1 downward. Opposing spin means 1 clockwise, 1 anti-clockwise. Note set of quantum number of each electron. No 2 electron has the same set of 4 quantum numbers. We have N, L, M, S. Okay, N, L, M, S. This is one set of quantum number. So no 2 electron has the same set. If they have the same N, same M, same L, they must have different S, different value of S. So first electron, positive half, second electron, negative half. Hund's rule. Electrons with equivalent energy or degenerate orbitals. Degenerate orbitals mean the orbital which has the same energy. For example, px, py, pz, they are degenerate orbitals. 3px, 3py, 3pz, they are degenerate orbitals because they have the same energy. We tend to occupy the orbital singly first before pairing up. For example, carbon, 6 proton means 6 electron. So we have to fill 6 electron in the orbital. We fill 1s first, 2 electron, 2s, 2 electron, so 4 electron in total. We need another 2 because 6 electron for carbon. So another 2 you must fill in 2p. We have to px, py, pz. You must label this 3 or 2p. Okay, so the 2 electron you must put singly first. 1 electron in px, 1 electron in py. You cannot put both electron in px. Cannot put both electron in one orbital. You must occupy the orbital singly first before pairing up. If you put 1, 2, 3 electron, the 4th electron, then you can pair. Okay, singly first before pairing up. This happens in the degenerate orbitals only. Okay, for orbital that have the same energy, px, py, pz, dxy, dyz, dxz, dx square, y square, dz square, those 5d orbitals, they are degenerate orbitals as well. An electron can fill any orbital of the same energy level. You can choose which one, it's up to you, but singly first before pairing up. Electronic configuration of atom magnesium, for example, 12 proton means 12 electron, so you must have 12 electron in total. 1s2, 2 electron only can occupy 1s, 2 electron can occupy 2s, so 4 electron in total. We need 12. And then 6 electron in total in 2p, 2, px, py, pz. And then now we have 10, we have another 2 you must fill in 3s2. And same for potassium. Potassium, 19 proton, 19 electron, 10 electron in 1s, 2s, 2p, and then 2 electron in 3s, 6 electron in 3p, here 6 electron in 3p, and 1 more electron in 4s. After 3p, 4s, not 3d. Refer here. After 4s, after 3p, 4s, not 3d. 4s first, then 3d. Follow this arrow. Main group atoms may lose or gain electrons, so as to form stable noble gas configuration. Noble gas configuration, 8 electron. Na, sodium, proton number 11. So proton number 11 means 11 electron. 11 electron. 1s2, 2s2, 4, and then 2p6, total 10, and then 1 more, 3s1. 11 electron in total. So in order for this atom to achieve stable octet electron arrangement or noble gas configuration, it must lose 1 electron. So if you have to draw the electronic configuration for Na+, remove 1 electron. The electron that you remove, this 1 electron, the electron at the highest energy level. So it becomes 1s2, 2s2, 2p6. So this number of electron is the same number of electron in neon atom. Same goes with F. F, 9 proton means 9 electrons, so 2 here, 2 here, and then 5 electron in P. So in order to achieve stable octet electron arrangement, you need one more electron into F because F is group 17, one more to achieve stable octet electron arrangement. If you add one more, add to the highest energy orbital. Orbital has highest energy, add the electron into that orbital. So 1s2, 2s2, 2p6. According to AUFBAU principle, 4s orbital is filled before 3d orbitals. This is because energy level of 4s orbital, before you filling the electron in 4s, the energy level of 4s is lower than energy level of 3d. Okay, the fact that 4s, you must fill 4s first before 3d, because if it is empty 4s, the energy of 4s is lower than the energy of 3d. However, electrons are always removed first from the ns orbital than from n-1d orbitals. Okay, if 4s are fully occupied by the electron, 4s has higher energy than 3d. If 4s orbital is empty, no electron at all, the energy of 4s is lower than 3d. If the 4s is full of electron, the energy of 4s is higher than 3d. That's why if you want to remove the electron, you must remove from 4s first, because 4s has highest energy. If we want to remove electron, we remove electron at the highest energy orbital. So orbital which has highest energy, remove electron from that orbital first. Anomalous filling pattern. Anomalous filling pattern is due to the unusual stability of completely filled 3D subshell. Two common examples, chromium, copper. So these two have unusual stability. What does that mean? Let's have a look at chromium first. For chromium, proton number 24, electron number 24 as well. So the electronic configuration, if we have to write the electronic configuration, we must fill the 4s first, because 4s has lower energy than 3d. So we must fill 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. This is what we predict according to AUFBAU principle. AUFBAU states that we must fill the orbital, electron must be filled into the orbital which has lower energy first. So orbital which has lower energy, when the orbital is empty, we want to fill the electron. If we compare empty 4s with empty 3d, the empty 4s has lower energy than empty 3d. So that's why we fill 2 electrons in 4s first, and then we fill another 4 electron in 3d. But this chromium, it doesn't follow the AUFBAU principle. This is anomalous case. The actual electronic configuration for chromium is 4s1 3d5. Electrons does not fully fill 4s. Just one electron in 4s and then the rest in 3d. Why is this happening? Due to the stability of the half-filled 3d5 subshell. If you take this one electron and you put in 4s to become 4s2, the one that we predict, if it is 4s2 3d4, we have one empty 3d orbital here. If we have one empty 3d orbital, this orbital is less stable than the orbital which is half filled with electron. Okay, if you compare 4 electron in 3D is less stable than 5 electron in 3D because there is one electron missing. This electron is in 4s. So if it is here, it is less stable. That's why this is the actual configuration for chromium, because it is more stable like this. It is more stable if you don't put one electron in 4s. If you have 2 electron in 4s and 4 electron in 3D, it is less stable. You must put 1 electron in 4s and 5 electron in 3D to make it more stable. That's what we call half-filled subshell. 1, 2, 3, 4, 5. All these orbitals are half-filled because fully filled must be 10. Fully filled 2, 2, 2, 2, 2, 10. So if all orbitals filled by 1 electron each, so this is what we call half-filled. Second anomalous case for copper. Proton number 29, electron number 29. This is the orbital diagram. The one that we predict, as usual, we must put the electron in 4s first because 4s, empty 4s, has lower energy than empty 3D. So we must put the electron in 4s first, then we can put in 3D. That's what we predict according to AUFBAU principle. But the actual electron configuration is it only one electron fills the 4s orbital. The rest fill 3D orbital. This is because the stability of completely filled subshell, because this is completely filled. 2 electron maximum for each orbital in 3D. 2 electron, 2 electron, 2 electron. This is what we call completely filled. Completely filled is more stable than you take 1 electron and put in 4s, make it 4s2. That is less stable. More stable when you put all 10 electron in 3D, make it completely filled. Leave this 4s 1 electron only. It is more stable this way compared to this way.